Good morning, guys. I'm going to ask you that I have just a second here to get the QCam thing set up, and we will get rolling. Okay. You see it? Maybe I need to restart the doc. Oh, or just plug it in. That could be the issue. All right, good morning, guys. So today we're going to continue our discussion of limits. Mostly today I want to do some problem solving and kind of make sure we're all up to the same speed. We're also going to talk about limit laws and some kind of more direct ways to go about computing limits besides just looking at graphs. Okay, that should work, but it's not. Sorry, so it seems like I'm having a little bit of trouble with the doc cam. Let me turn this off for a second. Maybe it's something to do with that. Oh, why aren't you working? It says it's connected. Maybe we'll try restarting it just one more time. Sorry about this, guys. Give me just one more second. The webcam, use this resolution. There we go. All right, just needed to be rebooted. Don't worry about this stuff. This is for my calc 2 class. So before we get started, like I said, today I want to talk a little bit about limit laws and try to get everybody comfy, or at least as comfy as I can, with those more direct mechanisms for computing limits. Before I jump into that sort of stuff, though, were there any questions from the homework that you guys have looked at so far that you're finding especially difficult or that you'd like to talk about a little bit? So if there are any questions like that, feel free to type them into the chat, and I can just pull the homework up. I know this first homework set isn't terribly difficult. There might not be any, and if there aren't any, that's okay. But I would always rather talk about one or two problems than just totally gloss over it. So yeah, is there anything like that? Any problems you guys would like to look at? This door. Question on tangent. Okay. There were a few questions in there. There's one that involves a sine and a tangent. So I think all of those had to do with the limit law stuff. plug. Sorry, so I'll turn off the screen share for now while I pull this up. Is that something we should be stressing about right now? Yeah, so I think the only place that the tangent function showed up was in the question asking about the sine of 5 theta over the tangent of 2 theta or something like that. I'll switch back to the screen share and we can go through this. We'll just share the whole thing, that's fine. So this question 6, I think is the one that was asked about in chat. They said to use a table of values to find the value of the limit. And if we have a graphing device, we want to use that to confirm the result graphically. So what do they mean when they ask us to use a table of values to estimate the value of the limit? What is it they're asking us to do? Look at that limit. We want the limit as theta goes to 0 of sine 5 theta over tangent 2 theta. So what should we do? What sort of table should we be making? Oh, why does that always disappear? Oh, because we got the screenshot. Yeah. Anybody have any idea what sort of table we should be making? So this is homework 1, question 6, and they want us to use a table to estimate limit as theta goes to 0.
Maybe 0.1, 0.01, and 0.001.
Yeah, think about the table of values that we use to approximate a limit on our lecture Wednesday. Right, we just put in a bunch of values for the variable that were close to this number, right? So here our limit is going to 0. We're sending theta to 0. So we should put in a bunch of values for theta into this function, sine 2 theta over tan 5 theta, that are very, very close to 0, and see if we can't somehow come up with a reasonable guess. Yeah, I can't plug 0 in. So remember what we said at the end of class last time. If possible, you always want to just go ahead and plug in the number that you're sending your variable to. So here, if possible, I would like to just plug in theta equals 0. So that's a good first step. I ask, can I plug theta equals 0? Remember here, if this function sine 2 theta over tan 5 theta was continuous when theta is equal to 0, then I could evaluate the limit just by plugging in. But the sine of 2 times 0 over the tangent of 5 times 0, that's the same as the sine of 0 over the tan of 0. Sine of 0 is 0. The tangent of 0 is 0. So what is this expression? 0 over 0.
Nothing.
Yeah, it's undefined. It's problematic, to say the least. It's problematic because the denominator is 0, right? If the numerator was 0 and the denominator wasn't 0, that would be okay. That wouldn't be a problem. But since they're both 0, we're in real trouble, specifically because the denominator is 0.
I have a question.
Oh, I'm sorry.
So,
A little bit. One more time?
I said I have a question. So what is the exact like idea process, like to think about, like what is it to mean undefined? Like I see that there's a hole on the graph, but I guess I really don't understand what its meaning is really.
That's a fair question. So the question is, what does it mean to be undefined? It means that I can't say from this expression what the value of this limit is. So the expression 0 over 0 could actually, what's the right way to say this? The term we use for it in mathematics is it's an indeterminate form. It's something you can write down, built out of numbers, that isn't itself a number. things that appear to be 0 over 0, like this, could actually be any real number. I'll show you what I mean a little bit later in the course. But the mathematical term for this expression is an indeterminate form, and we use that word indeterminate because things that appear to be this could be any real number. There are forms of 0 over 0 that turn out to be equal to 1. There are forms of 0 over 0 that turn out to be negative pi. There are forms of 0 over 0 that turn out to be infinity or 10 million. So it's the direct answer to your question, what does it mean to be undefined? It's not equal to any particular real number. And that would be true regardless of what's going on upstairs, just the bottom is 0. Any fraction where the bottom is 0 is defined, meaning there isn't any particular real number that I can say that this thing is equal to. And then particular expression a little bit more because the top is also 0. If the bottom was 0 and the top wasn't 0, there will be a way to make sense of that. Think about fractions where the numerator is close to 1 and the denominator is very, very, very small. Those fractions have very, very large value. If the top is not tiny, but the bottom is very, very tiny, then those are going to be fractions that are close to infinity. And we'll be able to make sense of that a little bit later in the course. But for us right now, I would say this is undefined because the bottom is 0. And what it means for something to be undefined is that there is no specific real number that I can say for sure that is equal to 0 over 0. So when you see 0 over 0, it could actually turn out to be anything. And that's what we mean by undefined in this case. Does that feel like a satisfying answer?
Yes, thank you.
Oh, cool. So I can't do this. Can I plug in theta equals 0? Nope. So let's look. This is the whole idea of a limit, is instead I don't actually care what happens at that point. I care what happens nearby. All that matters is what happens nearby. So let's look at theta values. Are not equal to 0, but are close to 0. And then if it's okay, I'm going to go ahead and hit the mute all here by default. If you would like to talk, then you can hold the space bar down to do so, just to keep background noise out. So we're going to plug in some theta values that are not equal to 0, but are close to 0, because that's what's going to determine the value of this limit. It doesn't matter what happens at that point, it matters what happens very, very, very nearby that point. And that's the crucial idea of a limit and the neat connection we saw with open intervals. So yeah, some ideas here. Let me call f of theta sine 2 theta over tan, 5 theta. So I can write my table in slightly more compact form. There's theta. And on the other side here, I'll have f of theta instead of having to write the whole thing. And the suggestions were like 0.1, 0.01, that sort of thing. Let's do that. So let's start with like negative 0.1, and then we'll look at negative 0.01, negative 0.001, and then we'll go to 0.001. We're skipping over 0 here. And we'll look at 0.01 and 0.1. All right, so here's approaching 0 from the left, and here's approaching 0 from the right. We're going to want a calculator or something like that for this. So I will pull up my virtual TI-83. Sometimes the old tools are the best tools. So you want sine 2 theta divided by tan 5 theta. So this is going to be sine of 2 times negative 0. Times, not yeah, times negative 0.001 1 divided by tangent of 5 times 0.1. And I get about 0.364. And if I look at negative 0.01, that's going to be the sine of 2 times negative 0.01 divided by the tangent of 5 times negative 0.01. That's 0.399. So sorry, let me move this so you can see both at once. I'll drag the calculator over, that's probably easier. So here I'm doing just what we said we're going to do above. I'm plugging in a bunch of theta values that are close to but not exactly equal to 0. And I'm writing those down in this table. So f of negative 0.1 was 0.364, and I rounded there to the third decimal place because we're just trying to estimate. F of negative 0.01 was positive 0.399. That's this last value. Let's keep going. The next one here on my table I said I was going to compute is f of negative 0.001. So that's sine of negative 0.001 divided by the tangent of negative 0.001. And that's looking like, ooh, that's a big jump there. No more 3s, just, I typed that all in right? Yeah, just straight up 0.999999. Okay, well, let's look at 0.001. So that's going to be the sine of 0.001 divided by the tangent of 0.001. And this is also that 0.99. And we know that 0 is right in here, right? 0 is right in between those two guys. So I'm stepping closer and closer and closer to 0 in my theta values as I walk down until here, and then we're going to be walking away. And these values look like they're getting very, very close to what number?
1.
Yeah, they appear to be getting really, really close to 1. If I wanted to, if I decide, oh, this is a little bit too coarse, I want to look even closer to 0, I could do that. And we need not even write it down. We could just go ahead and do this in the calculator for fun. Let's look at 0.0001. So there's, oh, wait, no. I made a mistake in this last calculation, didn't I? Yeah. I'm sorry. Ignore these last two calculations. I was wondering where those 3s went. I left out the 2 and the 5. Yeah. So let's come back to the negative 0.001 calculation. We need not the sine of that over the tangent of that. We need the sine of 2 times that. So the sine of 2 times negative 0.001 divided by the tangent of 5 times. Oh, this needs a multiplication too, doesn't it? Sorry, typing on this virtual calculator is a bit of a pain in the ass. By the tangent of 5 times 0. Okay. So yeah, this is 0.39999. And then I'll do this next calculation. 0 is still indeed in here. I don't know why I scratched that out. 0 is in between these guys. But I can't plug in 0. The whole point is that I'm trying to plug in things that are close to 0. If I plug in the positive 0.001, that's the sine of 2 times 0.001 divided by the tangent of 0.5 times 0.001. Yeah, so that's also that same 3.999, 0.3999964. Okay, sorry about that. So when I originally computed these two that you see scratched out here, I left out this 2 and I left out this 5 when I plugged in the theta values. And that's why those were coming out to being very, very close to 1 and not being super close to these guys. So this table makes sense, right? 0.364, 0.399, 0.3999964, 0.399999964. What are these getting closer and closer to?
.40.
Yeah, these appear to be approaching 0.4. Note 0.4 is the same as 4 over 10 is the same as 2 over 5. And you notice a relationship between those, right? The sine of 2 theta over the tangent of 5 theta, as theta goes to 0, is approaching 0.4, which is, as a fraction, expressible as 2 over 5. So there is a relationship between the numbers inside the sine and tangent there and the value that we're getting out of this limit. And we'll see ways to attack this directly a little bit later in the course. This can get a teensy bit complicated. So this is a good example of a limit to investigate by making a table because it's a limit that's kind of hard to get at any other way. They asked you also to confirm this with a graphing utility. We can do that briefly here if I pop up Desmos. This function is actually related to the sync function that we talked about last time. So we're really just interested in what's going on near 0, that's around here. And as you get closer and closer and closer to 0, you see that the outputs here are getting closer and closer and closer to 0.4. If I'm walking along the graph from the left towards 0, then my height is getting very, very close to this number. If I'm walking along the graph from the right towards 0, then my height is getting, again, very, very close to this number. But at 0 itself, just like the examples we were looking at the other day, this is undefined. Okay. So yeah, this is a good problem. Here's the table that we made. If you wanted to fill this out the rest here, you could. It's going to come out with these same numbers we had here. So I'll go ahead and write those in. So this would be 0.399 rounded the same way, and this would be 0.364. And so what you see is, yeah, as you get closer to 0, whether you're coming in from the left or from the right, you get closer and closer and closer to outputs being 0.4 or 2/5. So the main thing I wanted to talk with you guys about, with you guys today is some other approaches to finding limits. And I think because we just did this example, a fun example to start with there would be the one you saw me starting to compute accidentally. So what if I just had sine theta over tan theta? I could do the same thing, of course. I could build a table for this. First thing we should always ask is, can I just plug in theta equals 0? But we run into the same issue here. The sine of 0 over the tangent of 0 is still 0 over 0 is undefined. So no. Then we think maybe a table. But I say, nah, I'm lazy. You may not realize this yet, but mathematicians are profoundly lazy creatures. We really don't like to have to do work that we don't have to do. And if there's a way to get around doing something that is kind of painstaking like a table, we want to do that. And the main tool for us in this class is going to be algebra. So can I do some algebra? Well, let's look. So sine theta over tan theta, and I'll be good. I'll write my parentheses here, as you always should. That's the same as sine theta divided by sine theta over cos theta. Right? Because tan theta is sine theta over cos theta. And this is the same as sine theta times the reciprocal of this. And now I can cancel these sine thetas, and I just get cos theta. So it turns out without the 2 and the 5 absolutely change things. This is a totally different function than the one we were just looking at. I want to make that clear at the outset. Could not have done this with the previous problem. But if it was just sine theta over tan theta, we still have that same problem of not being able to plug 0 in. So if I want to take the limit, I still need some other way to get there. I could make that table, but I'm lazy, I don't want to. And so I ask, is there anything else I could do? And the answer here is yes, there's some algebra I can do. So if I rewrite tan theta as sine theta over cos theta, and then rewrite this division as multiplication by the reciprocal, I can cross out the sine thetas. Right? There's a factor of sine theta upstairs here, there's a factor of sine theta downstairs here, and they cancel. As long as theta is not exactly equal to 0. But remember, the value of the limit doesn't care about what happens at 0, it just cares about what happens nearby. So what we can conclude is, for all theta not equal to 0, sine theta over tan theta is equal to cos theta. Hence, the limit as theta goes to 0 of sine theta over tan theta is equal to the limit as theta goes to 0 of cos theta. And cos theta is continuous at 0. Sorry about my cat in here. Since cos theta is continuous at 0, this limit I can compute by plugging in 0 for theta. So the kind of question we're asking is, what happens as you plug in thetas that are really, really, really close to 0 in sine theta over tan theta? Do those values get really, really close to something else? We kind of a priori expect that they do get closer and closer and closer to 1. And then we can see from this guy, because these are equal, and this guy is equal to the cos of 0, which is 1, that this guy has to be equal to 1. And this is the kind of thing we're going to do most of the time when we need to compute a limit. If we can't compute a limit by plugging the value in right away, then we're going to try to do some algebra that allows us to cancel whatever factor is causing the trouble. So the trouble here was that we had 0 upstairs and 0 downstairs. And the thing that was causing that was the sign upstairs and this sign downstairs. Since I can cancel those, what I really am looking at here is a graph with a hole, just like the examples we looked at on Wednesday, right? Where there was a factor of x minus 1 top and bottom that we could cancel. Same sort of thing. There's a factor of sine theta that we can cancel, which is making the top and bottom equal to 0 here. So when I cancel that, I get the essential behavior left. I get the behavior of the function aside from what happens at that hole left. So everywhere except at theta equals 0, sine theta over tan theta is equal to cos theta. So that means if you want to know what happens as theta gets really, really, really close to but not equal to 0 in this expression, that's the same as asking what happens as theta gets really, really close to but not equal to 0 in this expression. This expression, though, is continuous at 0. So if you want to know what happens really, really close to but not equal to 0, you can just plug in 0, because he doesn't have the discontinuity that this guy has. And since they're equal everywhere except 0, including really, really, really nearby, the limit as theta approaches 0 for this has to be the same as the limit as theta approaches 0 for this. But this limit is easy to compute because he's continuous at 0. We just plug it in, and we get the value out. Nifty, right? So this is a good example. I know that our trig might be various flavors of rusty. I don't know when the last time was that everybody here had a trigonometry class. So I want to make sure you get this note, this example in your notes very, very clearly, and then we answer any questions you have about it before I move on and give you the formal limit laws. So what are we thinking when we look at this? What are we curious about? What are we bothered by? What are we wondering? What do we want to talk about?
You said we can't use calculators?
So on the exams, yes, it's unfortunate. So the official policy for this class is that you can use a scientific calculator if you would like to, but no graphing calculators.
Oh, cool. Okay.
So
Because I don't have the cos memorized. The cos 0 is 1. I forgot those things, so I just want to make sure I can plug in cos of whatever.
Those will be things that I expect you to remember. So
okay, that's okay. I can read.
Value of the cosine of pi over 4, you will need that. You will need that in this class on tests and things like that. So make sure you have your unit circle memorized, right? If that has drifted away, look back and make sure we get that back.
Okay, so it won't be anything outside of the unit circle.
Right, so I won't on an exam ever require you to give me an exact value of a trig function that is not known from the unit circle. Yeah.
Thank you.
Of course, no problem. Yeah. For like the last problem where we made that table of values, those were approximations, and you could use a scientific calculator for something like that. What else are we wondering? What else are we thinking?
I think I'm good. It looks good.
Feels comfy? Okay, I remember when I learned this, the thing that kind of blew my mind was that I was saying these guys are equal everywhere except at 0, and then I get this limit out by going ahead and saying fuck it and plugging in 0. That felt a little bit strange to me conceptually when I first saw this, and if there's a hang up there for you, I would like to try and alleviate that by giving us our first little theorem about limits. And this is the beginning of section 2.3. This theorem I don't think is given as a named theorem in 2.3, so I'm not going to officially start the 2.3 notes, but think of this theorem as the intro to 2.3. If f of x is discontinuous at 0, or at x equals a, let's say, and g of x is continuous at x equals a, and f of x equals g of x for all x aside from a, then the limit as x approaches a of f of x is equal to the limit as x approaches a of g of x is equal to g of a. So the idea behind this theorem is I'd like to take the limit as x approaches a of f of x, but I can't just plug in a because f is discontinuous at a. However, I know there's this other function g of x that agrees with f everywhere except at a, and g is continuous at a. Then I can get the limit I want, the limit of f, out as the limit of g, because these guys are equal everywhere except at that point. And then the limit of g I can compute just by plugging in, because g is continuous at a. So there will be a theorem similar to this that we do go through in detail when we get to section 2.5. But I think that this is the fundamental thing that's going on everywhere in section 2.3, although the textbook never states it. And I just wanted to show it to you as a kind of intro or primer to the section 2.3. So with that done, let's begin 2.3 in earnest. 2.3. This far in the book. So 2.3 is all on the laws of limits. Do they? I don't think they do. Yeah, no, they don't. That's okay. So this theorem, again, mostly an idea, right? It's something that I would like you to kind of try to get into your head, and it'll help you understand what we're doing in section 2.3. But it's not the sort of thing where you're going to have to cite this theorem in a problem. I'm never going to make you say, by this theorem, da 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 is true. It's just kind of an explanation as to why this stuff works. So if you're having a hard time like watching this video and understanding what happened here, try to really internalize what these words are saying, and then go back and work through this exercise again. We're going to start talking about section 2.3, which is limit laws. And the good news is that these are pretty much going to work exactly how you would hope that they work. In fact, some of this is almost not worth writing down. But in the same way that like you got to teach somebody how to walk before you can teach them how to run, you got to cover the very, very basic things. So suppose that that both of the limits. This is another theorem. So a theorem is a name in mathematics for a statement which is true. That's all. It's an important statement which is true. And they're usually phrased like if this, then this. So if the limits lim x to a of f of x and lim x to a of g of x both exist, then we got lots of stuff here. So make sure you've got lots of room on your page. Then the limit as x approaches a of f of x plus g of x is going to be the limit of f plus the limit of g. And I don't want to waste too much of your time here, but you can guess what would come next. The limit as x goes to a of f of x minus g of x. This is the limit of f minus the limit of g. Right, so if, for example, you had like a polynomial and you wanted to take a limit as x approached some number of that polynomial, you could just take the limit of each of the individual pieces, because those are all made of sums of simpler pieces, sums and differences of simpler pieces. The next has to do with multiplication by a constant. So if c is a constant, and you want to take the limit of c times f of x, that's the same as c times the limit as x goes to a of f of x. And these three together tell us that the limit operator is what's called a linear operator. You can split up over sums and you can pop out constants. Linear operators turn out to be hugely important. The limit operator is even nicer though. Not only does it allow for this, it also plays nice with multiplication and division, and that's what the next two things are about. So if you want to take the limit of a product of two functions, and when your book writes this, they're always writing these square brackets here to indicate that you're taking the limit of that whole thing. Most of the time in practice, we won't write those square brackets, but it's okay. This is equal to the product of the two limits. This is the limit as x goes to a of f of x times the limit as x goes to a of g of x. And that's the result for the product. The result for the quotient looks how you would think it does. And you can put it in these square brackets if you want. That's equal to the ratio of the limits. That's the limit as x goes to a of f divided by the limit as x goes to a of g. And this one assumes that the limit downstairs, because it's downstairs, can't be 0, right? This has to be different from 0. Okay, so these are the basic limit laws, which says that you can take limits of combinations of functions by taking limits of each of the pieces and then doing the natural thing to those limits. So if I've got two functions added up or multiplied or divided, I can take the limit of each of them separately and then add up the limits or multiply the limits or divide the limits. There are some kind of fun, silly questions in your homework that ask you to make use of these laws. I'll do one or two little examples built around those, but then we can deduce from these laws some slightly more complicated laws, and that's what's going to actually allow us to begin working in earnest with the more challenging problems. So let's look at one kind of fun example, and then we'll extend these laws a little bit. Before I do that, are there any questions on this on what this theorem is saying? So trig basics, I would recommend you learn for this class, all of it. It's all very, very important. There is no element from trigonometry that is not going to be important in this class. Calc 2 emphasizes your knowledge of trig identities more than anything else, and Calc 1 emphasizes your knowledge of trig graphs and the values of trig functions, unit circles, the geometric definitions. Those are the most important thing for us. So first step, make sure you know your unit circle. Make sure you know your unit circle cold. That's the very most important thing trig-wise for this class. Second thing, make sure you know the graphs, especially the graphs of sine, cosine, and tangent. Those are all over the place in this class, but so are the graphs of secant, and so are the graphs of the inverse tangent function, arctan. So make sure you know your unit circle and make sure you know your graphs. After that, I would say make sure you are comfy with the geometric definitions, the definitions in terms of triangles for each of the trig functions, all of them, all 6. And then after that, I would say you got to know your inverse trig. Make sure you know what arctan, arcsine, arccosine, right? The tan inverse, sine inverse, and cosine inverse functions are. Make sure you know how they're defined. Make sure you know the relevant domain restrictions. Those are the most crucial bits of trigonometry for Calc 1. Any other questions lingering? Okay, I'll try my best to keep my eye on the chat as questions come up. You can just type them in there. If you feel like some time has gone by and I didn't notice your question, feel free to shout out and say something. So I'm going to draw some graphs. And then we're going to use this graph to compute some limits. So we'll have this, sure, why not? 2. We're going to go out to 4. 4. And we can have f be discontinuous here. Fine. That's 1, 2, 3. So this is the graph of f of x. And then the graph of p of x will be similar looking. Well, we'll have this go. And then g does a little jump. Something like this. All right, so that's f of x, and this guy here is g of x. So g is the piecewise linear function, f is the curvy function. Neither one are continuous everywhere. G of x has this jump discontinuity. F of x has this hole that's been moved up here somehow. The y value at that filled in point up here, 2, 3. Okay. So I'd like to compute a few things. Let's find the limit as x approaches -2 of f of x plus 5 times g of x. And the idea is that I could get the limit of f and the limit of g on their own from the graph, but now I want this limit of a combined function. Any ideas what I can do algebraically to that expression, lim x goes to -2 f of x plus 5 times g of x? Think about the theorem we just wrote down. Remember, everything I write on the .cam is stuff that you guys need to be writing in your notes. So everybody should have this in their notes. If it's not all there yet, take a second, fill it in.
Wouldn't you want to split it up?
Yeah, I want to take this expression right here and split it up using these rules, right? So according to my theorem, this is equal to the limit as x approaches -2 of f of x plus 5 times the limit as x approaches -2 of g of x. All right, first I could say it's the limit of this plus the limit of this, but then the limit as x approaches -2 of 5 times g of x, that 5 can pop out. And now each of these guys, the limit as x approaches negative 2 of f of x, I can read from the graph. The limit as x approaches negative 2 of g of x, I can read from the graph. Yeah, so from here we need to use the graph. So what is this piece? What is the limit as x approaches negative 2 of f of x? So this is 1, this is 2, this is 3, this is negative 1, this is negative 2.
Would it be 3?
It's an interesting question. So f of negative 2 is equal to 3. But remember, the limit doesn't care about what happens at that point. It cares about what happens very, very nearby. So if I have my little dude trying to meet up with his girlfriend by walking along this graph, what's going to happen? Well, as the dude walks over this way from the left, and his girlfriend's walking over this way from the right, their heights aren't getting closer and closer to this value. They're getting closer and closer to this value, right? So it's the y value of the whole that this limit is discussing. And that's an important concept, right? It's that I don't care about what happens at the point. I care about what happens very, very, very nearby the point. And if I look anywhere nearby negative 2 along the graph of f of x, I'll be getting y values out that are close to 2, not close to 3. Because the graph has this weird jump here.
Okay, I see. So if it were like f of negative 2, then it would be 3 in that case, right? But if we're looking at the f of x, then it's going to be 2.
So when we're looking at the limit as x approaches negative 2 of f of x, that's going to be 2.
Okay, I see now.
Because the limit doesn't care about what happens at the point. It only cares about what happens nearby. So I'm asking, as I walk along this graph, getting my x values closer and closer and closer to negative 2, are my y values sneaking up on anything? And you can imagine if I was a little guy walking along this graph, yeah, my y values are sneaking up on whatever the y value at this hole is, which is 2. They're not sneaking up on this, right? These guys are way down here. They're not up there. So note, the limit as x approaches negative 2 of f of x is not equal to f of negative 2 here. Why? Because f is not continuous at x equals negative 2. We haven't talked about a precise definition of continuity, but I know that you all have an intuitive definition of continuity, right? Can you draw the graph without lifting your pen? And here, I can't draw the graph of f without lifting my pen, because specifically here at negative 2, there's this bizarre jump. So while f of negative 2 is equal to 3, the limit as x approaches negative 2 of f of x, that's equal to 2. All right, and now what about this other stuff? I've got my plus 5 times, what is the limit as x approaches negative 2 of g of x?
When you say as x approaches negative 2, do you mean from the right side or from the left side?
When we write the limit without the plus or the minus, we always mean both. So remember last time I said that the limit, the overall limit exists if and only if the left and right limits are the same. So here, when I say this, when I say the limit as x goes to negative 2 of g of x, I mean from the left and from the right. They have to be the same. This I'll even time.
Got it. Thank you so much.
Sure, okay, yeah, good. So as x approaches negative 2, along the graph of g of x, where are my y values going?
Negative 1.
Yeah, good, they're going to negative 1. So overall, the value of this expression is 2 plus 5 times negative 1, or 2 minus 5, which is negative 3. Not too bad, right? There are some sneaky things to watch out for here, namely this little observation, right? That this dot is different from the value of the limit there, and that the value of the limit is coming from the whole because it only cares about what happens nearby. It doesn't care about what happens exactly at -2. And then the question about one-sided limits. Do the one-sided limits agree? In other words, are these objects even defined? Do those things even exist? I think the next little example we wanted to look at is going to get at this idea. So let's look at one more. Let's call this part A, and we'll have a part B down here. And I look at the limit as x approaches 1 of f of x times g of x. My first step is going to be just like we did up here to split the thing up. I don't know what the graph of f times g looks like, but I know what the graph of f looks like. I know what the graph of g looks like. So this should be the limit as x approaches 1 of f of x times the limit as x approaches 1 of g of x. Now this guy, I'm not sure exactly what the y value of this point is. Let's say this is 1, 2.5. So then the limit as x approaches 1 of f of x would be what? What is this first piece?
Is it 2.5?
Yeah, exactly. Yep. Because the graph of f is continuous at x equals 1, right? As I walk through this point, nothing weird happens. There's no jump or hole or anything strange that I need to worry about. So the y value there is going to be the value of the limit. This one is 2.5. And I'm going to have to multiply that by the limit of g as x approaches 1. What am I looking at there?
-2.
This is an interesting question, right? So,
Oh, because there's 2, it's a piecewise. Okay.
yeah, it's weird. If I approach 1 from the left along the graph of g, then we go down to -2. As I approach 1 from the right along the graph of g, we go to -1. So this piece here does not exist, which means that the overall limit does not exist. Why does the limit as x approaches 1 of g of x not exist? Because the limit as x approaches 1 from the left of g of x is equal to -2, but the limit as x approaches 1 from the right of g of x, that's -1. Since the one-sided limits don't match, the overall limit, lim x goes to 1 of g of x, does not exist. Okay, so this is getting at what the question that was asked just a second ago. So in order for this object to exist, the overall limit without any little pluses or minuses written above there, that means that the left and right limits are the same, and they're both equal to whatever this value is. But here the left limit is -2, the right limit is -1, and since those are not the same, this limit right here does not exist. And so the limit I was asked to compute is 2.5 times something that does not exist. Well, if something does not exist, it's very hard to multiply it by 2.5. So the overall limit here, I would say, does not exist. having a hole does not mean that the limit does not exist. So look back to this limit, the limit as x goes to -2 of f of x. There was a hole here, but this limit still existed because as you approach from the left or from the right, both guys are getting closer and closer to the same height. So the important thing for a limit to exist is that when you sneak up from the left and you sneak up from the right, you're getting closer and closer to the same thing. So this idea of getting closer and closer, that's the big idea that we need to be wrapping our heads around as we learn about limits. As my x values get closer and closer and closer to 1 along the graph of g, what my y values get closer and closer to depends on whether I'm sneaking from the left or from the right. That shouldn't be the case. If the limit is going to exist, then as you sneak from the left and from the right, your y values need to be getting closer and closer to the same thing. So if your function does something different from one side than it does on the other, that's going to mean the limit at that point does not exist. Does this make sense? Right. So the left limit and the right limit must agree. They must be equal to one another. If they are, then the overall limit, the limit that we write without any little pluses or minuses on the top, exists and is equal to that shared value. If those two limits do not agree, then the overall limit, the one we write without the little pluses or minuses on top, just we say does not exist. Okay? So these are kind of cute examples that that allow us to get a little bit more comfy with the stuff we talked about on Wednesday, and also kind of give us an introduction to how to play around with the limit laws. The next thing I would like to do is to show you some slightly more advanced limit laws, and then we're going to play around with some of the good meat, some of the stuff that we're actually hoping to get to with our limits, namely algebraic tricks for evaluating limits. So your book writes each of these as separate rules. So these are some more limit laws. If you want to, you can think of this as a continuation from the previous theorem. If you have a whole function raised to a constant power, then this is the same as taking the limit of the inside and raising that whole thing to that power. The limit of a constant function is just the value of that constant. That's kind of boring. And this one you can probably figure out. If I take the limit as x goes to a of x, what do we think that's going to be? If you look along the graph y equals x, and you let your x values get closer and closer to 5, then your y values will get closer and closer to 5. And here, if you look along the graph y equals x, and you let your x values get closer and closer to a, then your y values will get closer and closer to a. A couple more. Number 9 is really what we get by combining number 8 with number 6. If the function x all on its own, as x approaches a, goes to a, and I can take a power of a limit like this, then this guy should go to a to the n. And I'll even write out a little explanation here, because limit x to a of x to the n, that should be the limit as x goes to a of x all to the n, which is a to the n, or just a to the n, like that. So there's combining rules 6 and 8 in order to get this thing your textbook calls rule 9. And see if you can understand exactly what it means to go from here to here, how we're making use of this. Right? Rule 9 is rule 6 with f of x equals x plugged in. And then rule 8 tells me that the limit as x goes to a of just x should be a. So if this is x, then this piece is this piece, which is just a. So here's the steps. Really what we're doing here is building up everything we need in order to take limits of polynomials and rational functions. Right? These are the building blocks for polynomial and rational functions. There's one more thing that we have here. Your book breaks it down into two things. I'll give it to you as the book gives it to you. The limit as x approaches a of the nth root, and again here n is a constant, of x. This will be the nth root of a, as long as a is positive, or as long as, if n is even, a is positive, as long as the root is defined. So of course I can't take square roots of negative numbers, right? I can't take even roots of negative numbers in general. So as long as the root on the right-hand side here is defined, this rule works great. And then the corresponding rule I want to take the limit of the nth root of a function. This works just fine. That will be the nth root of the limit of that function. As long as this limit is, again, as long as the root is defined. Okay. So these rules are what they are. Some of them are a little bit redundant, but each one is useful and meaningful, so it's worthwhile to play around with a little bit. I'll do one kind of trivial example, but then I do want to get to the fun stuff. One of these is an example we've already done. So if I want to find the limit as x approaches -2 of x cubed minus, or plus, sorry, 2x squared minus 1 all over 5 minus 3x. I can do this by breaking that thing up and just taking the limits of each piece individually. So I'm going to do this once very, very carefully, but only once. This is according to my, what was it? By the numbers here. According to my fifth limit law, this should be the limit of the top. Divided by the limit of the bottom. And then the limit of the top, I can split into 3 limits. That's the limit as x goes to -2 of x cubed plus 2 times the limit as x goes to -2 of x squared minus the limit as x goes to -2 of 1 all over the limit as x goes to -2 of 5 minus 3 times the limit as x goes to -2 of x. In practice, we will never do this, but we're doing it once to show you that the laws do work, and then we'll conclude something nice that will allow us to save a lot of time in the future. Any questions about what I've done here so far? So I started out with a limit of this big ratio, this big fraction. And rule 5 says you can take a limit of a big fraction by taking the limit of the top and the limit of the bottom separately. So if you want to write in those square brackets, those look like this, to make everything look more and more like our limit rules. But then the limit of the top, this involves 3 different pieces, all added and subtracted. And it also involves some multiplication by constants. And my first few limit laws 1 and 2, limit laws 1, 2, and 3, so you can take the limit of each of those pieces separately, and also you can pop out the constants. So I do that top and bottom. And then according to limit law 9, the limit as x approaches -2 of x to the 3 should just be -2 to the 3. And then I've got this plus 2 times the limit as x goes to -2 of x squared. Well, that should be -2 squared minus the limit of a constant. Here, this 1, that's a constant function, is just that constant. And then downstairs, what do I have? I've got the limit as x goes to -2 of 5. This is again a constant, so that will just be 5. Minus 3 times the limit as x goes to -2 of x is just -2. Now compare the bottom line to the top line. What did we end up doing?
We plugged in -2 as x approaches it.
Yeah, all we did was, this is just what you get when you plug -2 into everything here, right? Everywhere there's an x here, you now have a -2 here. That's all we did, right? We just plugged it in. So the lesson that we should learn from this is that if you're looking at a rational function, that is a ratio of 2 polynomials, or just a polynomial function, a consequence of our limit laws is you can always calculate those just by plugging them in, as long as it doesn't make the bottom 0. As long as the number that you're trying to send x to is not a number which makes the bottom of your function 0, then you can just plug the damn thing in. And you'll get the same thing you would get by very carefully, one step at a time, applying your limit laws. Let's go ahead and do the computation. -2 cubed is -8. -2 squared is +4 times 2 is +8. -1 is -1. Downstairs I have 5. Minus 3 times -2 is 5 plus 6. So this is -8 plus 8 is 0, minus 1. 5 plus 6 is 11. So this is -1/11. And we got there just by plugging in, right? What we actually did was very, very carefully go through our limit laws. But what we ended up with is what you would have gotten if you just plugged -2 in for x. And that works great. That works wonderful, as long as it doesn't make the denominator 0.
Question. So what if the denominator is 0?
Yeah, that's a good question. So to answer that question, let me return, we can kind of build up to it, because the denominator being 0 isn't the only way things can go wrong. But yeah, perfect, wonderful question. What happens if the denominator is 0? Well, then we're in trouble, right? Then going through this process wouldn't save me, because going through this process always leads to the same thing you get when you just plug in. And this is the how do you say, punchline for today's lectures, is what do you do if you can't just plug in? So let me write this down first, and you should write this in your notes too. I know it seems silly to write all of this out, but please do so. So 2 observations. We ended up by following the limit laws. With the same thing, we would get just by plugging in x equals -2. So do that. Instead. Right? What we just did here is like building a house by first going down and cutting the trees, and then digging up the iron ore to manufacture the nails, and then going to college to become a draftsman, right? This is like a bunch of unnecessary, overly detailed stuff that leads us to the same shit you would get if you just went to Home Depot. So just go to Home Depot, right? Just plug it in if you can. However, we can't always do that. We can't always just plug in, because sometimes my function is undefined, i.e. the bottom might be 0 at that point, or my function might be defined in some way that plugging in doesn't give you the same thing as the limit. Are we able to plug in x to get the limit if it was +2 plus or 2 minus? If you were looking for a left or a right limit, yeah, it would have worked out the same. Now, in practice, the left and right limit thing is something we only really check if we're doubting that the overall limit exists. So for a polynomial or rational function, left and right limits will always exist and will always agree, because those are functions that are continuous everywhere aside from where their denominator is equal to 0. But yeah, if you were trying to calculate a left or right limit for a function like this, a polynomial or rational function, then you could also get there just by plugging in. That's a fair question. But what I'd like to look at now is something where we can't just plug in. I'm going to look at 2 ways that can get messed up. So let's define the function g of x piecewise to be x plus 1 if x is not equal to 1, and to be pi if x is equal to 1. Hopefully your pre-calculus class was strong enough that you could draw me a good graph of this function. Can anybody describe the graph of this function in just a few words for me? For the most part, this function looks like what?
It's a time piece function, right? Or a time something.
Yeah, this is a piecewise function, and I saw it in chat. For the most part, this looks like a straight line.
Yeah, that's right.
This looks like the line y equals x plus 1, with one exception. When x is equal to 1, instead of y being what it should be there, we're up here at pi. Okay, so my y-intercept here is 0, 1. This point would be at 1, 2, except there's a hole there because this function only behaves like x plus 1. So this is the line y equals x plus 1, except here where there's a hole, because it only behaves like x plus 1 if x is not equal to 1. When x is equal to 1, it takes the value pi. So here, what is the limit as x approaches 1 of g of x?
Two.
Good, it's 2. Because if I'm looking very, very, very nearby this hole, but not exactly at this hole, my y values are getting closer and closer and closer to 2. But this is not equal to g of 1, is it? Because g of 1 is pi. So this is one case, this is one fashion in which plugging in doesn't always work. If you tried to calculate this limit by plugging in, then you would get pi out, because g of 1 is pi. However, this function is discontinuous at 1. And so that pi value isn't related to this limit. Remember, the limit, don't care what happens at a, they care about what happens near a. So this limit doesn't care what happens at 1. At 1, g of x is equal to pi. It cares about what happens very, very nearby 1. And very, very nearby 1, g of x outputs values that are very, very close to 2. Bueno? This is one of the first intellectual hurdles of Calc 1. So it's important that we spend a second really, really wrestling with this. What are we thinking or wondering about this? Which is a. So in this example, I've been using the notation limit as x goes to a. So a here, this is, I'm referring to in lim x goes to a. So a is the place where I'm trying to send x in my limit. So in this example here, a is equal to 1. It's the place I'm trying to send x. It's the place I'm trying to take the limit. Okay. I do want to look at one more example today. The next example in the textbook is one that we've already done. So I'll say recall. The limit as x goes to 1 of x squared minus 1 over x minus 1. I can't calculate this by plugging in, because if I plug in, I get 0 over 0, which is no good, is equal to the limit as x approaches 1. So we're still answering the question, what happens if you can't plug in, right? How can that plugging in method fail? And this is the one that fails in the most obvious way because it makes the denominator 0. But if I factor that numerator as x plus 1 times x minus 1, then I can cancel the x minus 1s. And then I can plug in, and I get 2. So remember, this was another example of a function whose graph had a hole. The graph of this function looks a lot like the graph of the function we were just looking at, only instead of having a hole where the value has been supplanted and moved up to pi, it just has that hole. So this is what the graph of this function looks like. Well, here, the idea is that in order to calculate this limit, I needed to get rid of the x minus 1 downstairs. Because if I try to plug in 1, then the downstairs would be 0, right? 1 minus 1 is 0. So I can't plug 1 into the expression as it is. If I try plugging 1 in here, I get 1 minus 1 over 1 minus 1, which is 0 over 0. And because the denominator is 0, that's undefined. So I had to do something to get rid of the x minus 1 downstairs. And for this function, the something which worked is factoring the top and then canceling that factor of x minus 1 that was common to the top and the bottom. All right, I know we're going a little bit over time. I'm going to ask you to be patient with me because this last example is important. If this example is bothering you, I wrote recall, go back to the video from Wednesday, right? We worked this one out very carefully on Wednesday. So the last example I want to play with has the algebraic shape of some stuff we're going to be playing with a lot very soon. And you may recognize things looking like this from pre-calculus when you were told to write down and simplify some difference quotients, right? Some a plus h stuff. This looks a lot like one of those, and there's a very good reason you were made to do that in pre-calculus, because now we want to send h to 0. Right? If you took pre-calc with me, then we talked about that. But either way, this is the task. Observe that if I plug in h equals 0, because it makes the bottom 0. So the whole thing would be undefined. However, I can still take the limit. And the key to taking the limit is going to be doing something like what we did here, where we're able to factor and cancel the problem term out of the denominator. So here's how we do this. I'm going to square this out. 3 plus h all squared, that's 3 plus h times 3 plus h. Remember to FOIL, right? And I'm not actually doing anything with the limit yet, but I'm still going to write it at every single step. Otherwise, these things won't be equal to each other. So good notation is very important. It's one of the things you must develop in Calc 1. Be disciplined about what you write down. Don't fuck around with this. Write every step. Make sure what you're writing every step is true. I'm putting equal signs between these, which means I need to write the limit. I can't skip writing the limit. Now I'm going to FOIL my 3 plus h times 3 plus h, and I get 9 plus 6h plus h squared. And then that minus 9 is still there. And this is all over h. And notice what happens. Something nice happens. This 9 and this 9 cancel. So I get 6h plus h squared over h. And so far, I haven't canceled anything. All I've done is manipulated this algebraically. I just FOILed that out. So these things are definitely equal to each other. Now in my next step, I can factor an h from the numerator and cancel it with the h downstairs, very similar to factoring this numerator and canceling the x minus 1s. Take seriously what I said about good notation. Never get lazy and stop writing your limits. Never get lazy and stop writing any piece of these things. Your hand will get tired, deal with it. Mathematicians have strong hands. When I factor an h here, I get h times the quantity, or parentheses, 6 plus h, all over h. And now you can cancel these. So this is the limit as h goes to 0 of 6 plus h. You can write over 1 if you want to, but something over 1 is just that thing. And now this piece is continuous at h equals 0. This is kosher as long as h is not equal to 0. Here we're using the theorem that we talked about at our little introduction to section 2.3. If you have two functions that are equal to each other everywhere except at one point, then you can take the limit of those two functions and get the same thing. This guy I can take the limit of by plugging in. This guy I could not. Because I'm able to cancel this h though, that means that this guy is just 6 plus 0, which is 6, has to be the same as the limit of this guy. So this limit, which I could not get by plugging in because it made the bottom 0, which is undefined, can still be calculated by doing some algebra and canceling the h from downstairs because he was the problem factor. So This is the general approach that we're going to need in order to start talking about the things we want to talk about deeper in this calculus class, specifically the derivative. This thing is a rate of change. It's an instantaneous rate of change. Rather than having two different points and finding a slope, we're finding the slope at one point, which is a very sneaky thing. We're going to talk about the geometry of that later. We're going to worry about the applications and the rate of change stuff a little bit later, because I know that in Calc 1, one of the things people struggle with is just the mechanics, the algebra here. So study this example. Make sure you understand this example. Look in the textbook. If you don't have a copy of the textbook that you like yet, please reach out to me. I can get you a PDF. Once you're into WebAssign, you do have a copy of the book there, which works. That's great. But if you hate that copy, that's okay. I understand. I kind of hate that copy too, so let me know. If you would prefer a hard copy, again, let me know. I can probably help you find one for cheap. But make sure that you are leafing through the textbook a little bit. So leaf through section 2.3. Pay attention to the examples. The examples are very good. We did a few of them here today. We're going to do more of them later. And it will help you having seen the examples beforehand. Continue working on the homework. The homework doesn't have anything that's going to fry your brain too hard. It gets no harder than this, I promise, for this week. And it is due on Monday. So if you haven't started that homework, you need to start it today. You need to start it like right now. And then you need to work on it over the weekend and get it done by Monday. If you don't get it done by Monday, don't stress or freak out. You can submit an extension request and I will grant it. But you really want to start out on the right foot. This class starts gentle and builds really fast. So this is the gentle start. Get ready for it to start building fast. And yeah, remember what I said about the text. If you would like some help obtaining a hard copy or a better soft copy of the text, send me a Canvas message or an email, and I'll point you in the right direction. Okay, thank you guys for hanging around. If you could, before you go, just go ahead and type the word "here" in chat so I can keep a reasonable log of attendance. And then you are welcome to sign out for the day. I do have an office hour today. It's not next hour, but a little bit after that. And the links for that are in Canvas on our homepage, okay? So if you want to chat about any particular problems, you have any questions, come by the office hour. Otherwise, I will see you guys on Monday. Remember to work on the homework. Alrighty. And once you have typed here in the chat, you're welcome to sign out. I'll give just a few more seconds for that, but then I will end the meeting. So make sure you do so soon. Alrighty.